Hi everybody, welcome back to Chem 140. We don't really have all that much content left to cover, so that's good. We'll definitely finish it. But there is quite a bit left to do between now and then. So let's see here. I don't know if I actually have quiz. I might be missing a quiz due date on here. Hold on. Let me look this up real quick. Yeah, there's something due, tomorrow. So let me add that real quick. So there it is. So we got quiz number 8. That's units 13 and 14. That's due tomorrow. Ooh, there seems to be an issue here. Hold on. Yeah, it's due tomorrow, but it closes on Wednesday. I had it close on Tuesday. Oops. Yeah, I fixed that now. So that will be tomorrow's is a soft deadline. It closes on Wednesday. I'll open it up for Thursday so you can study for it for Friday. There is a quiz 9. Quiz 9 is worth 1 point. It's basically a practice quiz. I'm going to open that up tonight. I encourage you to do it before exam number 2, but if you don't, like, whatever, it's 1 point. Everybody gets the 1 point because there's a question in there where you check a box that says, give me 1 point, please. And then all the other questions are worth 0. I can't make the quiz out of 0 because Canvas won't let me. So this is what I do. So yeah, you'll have some content to practice on for the exam that you'll see on the exam on Friday. Just a brief overview of, again, what's going on this week. So lecture today, lecture tomorrow, review on Wednesday, exam number 2 on Friday. Something else that is also available is if you have been reading the announcements, and I assume everybody reads every word that I say of the announcements all the time, and that you have them all memorized, and yeah, no. Here's the announcements page that you've probably never seen. I do send these out via email. Excuse me. So hopefully you've checked your email. But this is the announcement. So there is course evaluations this quarter. They are due Friday the 11th at 11:59 p.m. And then they close, and then they're closed forever. And I can't open them because it's not mine. If you follow this link, it will take you to this page where it will direct you on how to do the evaluations. Here's the login link. It will show you what it looks like. It tells you about what your credentials are. If you have issues logging into the campus labs page, and every quarter I get like 20% of my students emailing, I can't do the course evaluations. It's not accepting my password. I can't help you. So what you'll have to do here is you'll have to either reset your password down here at the evcc/my account reset terminal, or email Peg here, who is in charge of all of the evaluations, to ask her for more information. Like, why isn't my password working? Because every quarter this happens, and I don't know if they fixed it or not. I email IT constantly, and they direct it to whoever is in charge of it, and I actually don't know who it is because this isn't my purvey. I don't have access to your credentials. Like, I don't know what your password is. I don't know what your login is. I don't have any idea. I can't do anything about it. So don't do this at the last minute on Friday, get stuck, and then go, well, I tried to take the evaluation. Does it count? No, it won't count because there's no evaluation. Do this early in case you hit an issue, okay? Because I know you guys do everything on time. There's not a single one of you who's ever turned in something after the deadline. Never. I'm saying with a straight face. I've seen all of your labs. They all say late. I don't care, but, like, you know, you guys can do things ahead of time, right? Yeah, do this one ahead of time because it's worth extra credit if you do it. 10 points. That's a whole quiz. Now, if I get at least 80% of the respondents filled out, and that I can see. I can see how many people have responded, just not who or what the responses are. I will give everyone 10 extra credit points. If I get less than that, I give less extra credit, and it scales down from there. So, like, if half the class did it, I might give you, like, 2 points. So, try to hit that 80% deadline. No witch hunts. Do not pester people in the Discord, like, have you done the evaluations? Do not threaten anybody. I will cancel your extra credit. Do not do that. I have had a class before where one student, this is when I was teaching in person, this is at Tacoma, and she stood in front of the doorway with her laptop and would not let other students in unless they told her they had done the evaluation. And if they hadn't, she was trying to make them do that in the doorway, making everybody else wait. And I was like, nope, that is not okay. You no longer are eligible for extra credit because that is harassment. Do not harass other students, okay? Just do the evaluations, please, if you have time. And I'm willing to bribe you to do that. Now, you might have noticed, wait a second, weren't these open in May? Yeah, they totally were. I only give you guys a week to do this because if I open them in May, everybody forgets and nobody does them. So now you have a week to do it. Do it tonight after the lecture or after you've watched this video, and just go quickly fill out the course evaluation. I answer the evaluations candidly and honestly. Note that there will be questions on there that are completely irrelevant to this class. No, we did not foster artistic ability and creative skills. No, we did not talk about ethics. Like the evaluations are supposed to be one size fits all. Don't assume like, oh well, I mean those are important topics, so we only sort of kind of did them. No, I'm very specifically trying to get evaluations on specific categories. I'm not going to tell you what those are, obviously, because that would influence the evaluations unfairly. Let me close this, and then I will answer that question that's there. So, is the quiz 2 attempts or still unlimited? It's still 2 attempts. But you do get to see the answers immediately after, because it is not a graded quiz. So it's not going to be a wait until everyone's done thing. It'll just, you take the quiz, it'll score it right or wrong, it'll be out of 0 for those questions. But you can see the answers immediately. And you can totally ask me any questions you want about Unit 15 and 16 on any day except the day you were taking the exam. So if you ask me on Friday, hey, I got stuck on this question on quiz 15, or the chapter 15 quiz, can you help me go through it? I will say I have to wait until tomorrow. The Lewis structures are very artistic. I hope you like them. I worked very hard on them. But I did not evaluate or assess them for like your line strokes or the quality of the dot on the eye on lithium or things like that. So yeah. Okay, so let's do the last unit. The last unit is about solutions and solubility and the math that we do with it. This is also going to be very relevant for the last lab, which we're going to talk about tomorrow, because we need to understand everything in this section in order to talk about the lab. And normally I actually teach this section in the lab, like we would have been doing this weeks ago, the first few parts of this, so that you can make a solution, and then the next lab session we would use the solutions and you do the titrations. Now, unfortunately, we don't really get to do that in an online setting. So we're going to try and mimic that the best that we can. But it does mean that lab number 5 does sort of get tacked on the end as a sort of just like afterthought. And there's a lot to lab number 5, which is why I'm going to grade it very, 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 very liberally. Like if you attempt it and you get even sort of close, I don't even care about sig figs. I'm just going to look at it and be like, okay, that's close enough, and give you your 25 points for it. More on that tomorrow. All right, so let's get started. Many people have done this experiment before. This might be my shitty video. Let me check really quick. Oh no, I got a better video. Okay, good. I had an old video that I hated. It was clearly made by like some sort of high school student for a project, and it was just Windows Video Maker, my first video, so we don't need all of these extra videos on the side here. There we go. All right. So what we're going to be doing is adding sugar cubes to these containers. And I think there's a little bit of sugar in there already, but here we go. When you add sugar or salt or something that dissolves in water, you can see that it starts to deteriorate away. Now, the sugar isn't just gone. It doesn't disappear. The conservation of mass is not violated. The sugar instead is present in the solution around the cube, and it will slowly melt over time. And if I do this, if I just accelerate forward a little bit, you could see it just kind of disappear rather quickly. The one on the left is hot water. The one on the right is cold water, and you can see that the hot water dissolves it much more quickly than the cold water does on the right there. So when you add a substance to water, and that substance is soluble, it dissolves. And you can't see it anymore, but it is still there. It exists as individual particles. So something that dissolves is called soluble, but something that does not would be insoluble. Now, an example of something that's insoluble is if you go outside and you put mud in water. The mud sinks to the bottom, and you could swirl it around all day, but the mud will just sink and it will sit there. Some of it tries to dissolve as the water gets brown and murky, but for the most part, the silt and sediment settles to the bottom. All substances that we're going to deal with in this class and in chemistry in general will be either insoluble or soluble in a liquid medium. We're going to be using water for almost the entirety of our solutions here in this class and later classes, but you can use other liquids. In fact, sometimes you have to. For things like medicine, some medicines are insoluble in water, so you have to add something that is biologically safe, such as like ethanol, to help it dissolve. Now, when you make a solution, the solution is the dissolved thing into a liquid. You have two parts, and we got to give them names. The first part that we're going to name is the solute. The solute is the substance you're dissolving. So I am dissolving the solute. And it goes into the solvent. And it's the stuff that we're going to dissolve things into. I was going to write I'm dissolving into, but then I thought, oh, I'm not dissolving. The stuff is dissolving. Okay, so you put the solute into the solvent. Now, there is a way that you can define which is which, because you could do this in either direction, right? I could pour the water on the salt, and it would be kind of a question of, okay, which one am I dissolving into which one? And the way that we go about defining that is that we do it by amount. Whichever one there is more of is the solvent, by definition. Whichever one there is less of is the solute. Now, if you land exactly on 50-50, it's ambiguous, but in almost every other case, we won't have a 50-50 solution. There will always be one there's more of and one there's less of, and the one that there is more of is the solvent. Now, technically speaking, solutions that we are going to be dealing with primarily exist in the domain of the solvent is a liquid, but that's not the only possibility that's out there. In fact, any homogeneous mixture is defined as a solution. For instance, the air that you are breathing right now contains oxygen and nitrogen and argon and water vapor and carbon dioxide. Of those, the solvent, which is the most abundant one, that would be nitrogen. And the solutes would be everything else that's in there, etc. If you're drinking carbonated water, like I do all the time, I just finished this can, I'm going to have to get another one. The solute in carbonated water is CO2. It's dissolved into the water to make it fizzy. If you're drinking just regular water, you have oxygen or air or other stuff dissolved in the water. Oxygen dissolves into water so that fish can breathe. Well, that's not why it does that. But as a consequence of oxygen dissolving in the water, fish can use it, and they swim around, and that's why they like cold water, because oxygen's more soluble in it. We're going to talk about solubility of all of these things and how much dissolves in there in just a second. These three are the most common ones where, oops, that was the worst squiggle ever. There we go. It's not much better, but that's fine. These are the ones that we're going to be dealing with the most, primarily the bottom two, where our solutes are either liquids or solids. Now, you can have solid solutions, like we talked about. Wow, I just cannot draw this low on my tablet here. You can have solid solutions, like we talked about very early in the quarter when we were talking about homogeneous mixtures with alloys and stuff. Alloys are examples of solutions where the solvent and the solute are both metal. So this would be things like steel. Shown is electrum. Electrum is silver dissolved into gold. But you can also have liquids or gases dissolved in solids. A little bit harder to do, but you can still do it. Mercury, for example, is insidious. It will seep into any metal and form an alloy. It's harder to get gas into a solid and keep it there, but it does do that too. We're not going to encounter those other than alloys, and we're not even going to do chemistry with them. How much stuff dissolves in a given solvent? Right here I have... Oops, I got to hit escape here. I have a solubility table, so I'm going to call up Wikipedia here. We'll get... Not the timer. I don't know why it keeps bringing that up, so... So what we have here, this is Wikipedia. This is the solubility table for all known substances that have been measured. And let me try and make this a little bigger so that you can actually see the numbers here. There we go. This is just A. So this keeps going and going and going. There are a lot of substances whose solubilities have been determined. And you'll notice that primarily one temperature has all the data filled in, and that's room temperature, 20 degrees Celsius. For the most part, the vast majority of solutions that are formed become more and more soluble as you increase temperature. So if you look from left to right at virtually any of these, solubility goes up as you heat the solution. Now, that's not universally true. There are some solutions that become less soluble as you heat it. And there are thermodynamic reasons for that that we're going to discuss in Chem 162 just a little bit. But for our purposes, almost universally, things increase in solubility as you heat them. So when you look at this chart that I've stolen from another textbook, you can see that that trend is, for the most part, true. Now let's look at the axes on these graphs here. On the y-axis, I have solubility measured as the amount of salt in 100 grams of water. So we're just using 100 mils of water here. Density of water being real close to 1. So 100 milliliters of water, how much can I dissolve in it? On the x-axis is the temperature. And so what we're going to do is we're going to fiddle around with temperature and explore various traits and try to explain it a little bit. I don't like these definitions terribly much because we're not going to refer to them in terms of numbers. And when you guys see numbers, I know the first thing you want to do is, oh, we're going to use this as a hard and fast scale. And not really. So the following terms are the ones that are major. So insoluble and soluble. Oops, I didn't want to do that. I thought there was one down here. We don't really use slightly soluble. This is not really something that we care about. In 163, when we talk about solubility product, we're going to come back to the idea of slightly soluble, because technically everything is slightly soluble. But the threshold for insoluble is having less than 0.1 gram dissolve in 100 grams of solvent. Again, that's sort of arbitrary, and you're not going to need to remember that, because you'll look at something, just drop a chunk of it into water. Did it go away? If the answer is no, it's insoluble. Nobody cares about how much dissolves, right? Later on, again in 163, we'll talk about things that dissolve to like the 10 to the minus 5 grams level, or 10 to the minus 7 or 8 or whatever, depending on what it is we're looking at. But the vast majority of substances that we're going to examine dissolve pretty readily in water. So more than 1 gram on our chart here would be anything higher than this mark right here. And so you can see that's virtually everything that we're testing. So again, don't worry about these thresholds. Not important. Just soluble or insoluble. All right. My picture didn't appear before my tooltip did. Some other terms that go into defining solutions are in terms of their saturation. A solution that is saturated has all the solutes that can be dissolved at that temperature. Any extra solute that is added can't dissolve. There's already too much in the solution. That solution sits at the bottom of the container and makes it look like it's insoluble, but you can very clearly see that some of the solute has dissolved because the liquid is very, very blue. This is copper sulfate, by the way. Copper sulfate will dissolve into water, but its solubility isn't amazing, and so you can eventually reach a saturated solution, and the rest just sits at the bottom. The reason for this is because as my solute dissolves, it enters the aqueous phase. And so this would be my solute. These red dots are what is causing the color of the solution. I would use blue, but you wouldn't be able to see the dots. Now, eventually, I get so much solute up here in the liquid phase that it will, on occasion, bonk back down here and then recrystallize. And as more and more of this populates the top phase, the likelihood of this happening increases. Until eventually they are dissolving and recrystallizing at the same speed. Adding more solid doesn't affect how quickly it dissolves into the solution because the only place where dissolving can occur is where it contacts it. That would be the surface at the very top. And the surface area wouldn't appreciably change if I added more. So we reach a sort of equilibrium where stuff dissolves and then undissolves at the same speed. That state is called a saturated solution. Now, what if I only add a tiny amount into that? So then what would happen is if I added a small amount and it dissolves, and then once all of the stuff that was down here is now in the solution, not as much of it because we didn't add as much, this part disappears and we're stuck in this state. Now, if my solution wanted to recrystallize and go back to a solid, there's really nowhere for it to start crystallizing. I need a crystal present for this to occur. If I have dissolved everything in there, I could put more solid in there and have it dissolve. But it will not recrystallize and precipitate out of the solution on its own. We're going to call that solution unsaturated. So a saturated solution has as much as can be dissolved in the solution at a given temperature. An unsaturated solution has less than the maximum. So we can go back to this chart, and we can pose some questions here. So don't worry about this up here just yet. But let's suppose that I was going to look at KNO3. So here's KNO3. I'm going to take the felt tip pen here. We're going to draw the KNO3 line real thick. There you go. Thick with 2 C's, right? Wait, that's not what that means. All right. So now that we've got this line here, let's suppose that I'm working at 20 degrees Celsius. And I put in 15 grams of potassium nitrate in 100 grams of water. if this was the solution I made, so there's my water, and I put in 15 grams KNO3, whoop, into this beaker it goes. This is what I would expect to see. It should all just dissolve, and there would be no solid at the bottom, and so the result would be unsaturated. Now, let's suppose that instead of 15 grams, I instead put 50 grams in. Again, this is at 20 degrees Celsius. If I put 50 grams in here, I've put way too much. The most that this solution can hold is 30 grams at this temperature. So, some amount would just sit on the bottom. Roughly 20 grams would be undissolved, and the part that would be dissolved would be roughly 30 grams. And that solution would then be saturated. Now, if I put exactly 30 grams in there, I reach this sort of equilibrium where everything perfectly dissolved, and if I added even a little teeniest, tiniest speck, it wouldn't dissolve. So that would happen if I got really close to the line. But we're going to use examples that are more obvious so you don't land on a situation where you're like, oh, I don't know what happened because I'm so close to that line. All right. Now we're going to do a different experiment here. You know what I'm going to do? I'm just going to do this. And this experiment is going to involve us preparing a solution and then changing its conditions. So here's what we're going to do. We're going to heat a solution up to 50 degrees Celsius. And according to this, I should be able to add 90 grams of KNO3. So I'm going to do that. So I'm going to have a hot beaker of water. With no holes in the side of the beaker. And I'm going to dissolve 90 grams potassium nitrate. And so there's going to be tons of the stuff in here. And we're going to set it up such that there is no visible solid at the bottom. So I might add just a little bit less than 90. Just to make sure that I have an unsaturated solution. So this is at 50 Celsius. Then what I'm going to do is I'm going to allow this to cool down to room temperature. And so at 20 degrees Celsius, you would say, oh, okay, well, I would expect that this would happen. Here's my beaker again. And that a bunch of this is just going to become solid and precipitate out at the bottom. And then the remaining 30 grams is going to just be up here. So here's about 30 grams. And here's about 60 grams. That's what we would expect to happen. But remember, we can't crystallize out of solution unless there is something to crystallize onto. So what actually occurs at 20 degrees Celsius is that everything stays dissolved. And so we end up here. So the syrup question that you have there in the chat, that has to do with viscosity, and it's similar to this. We'll talk about viscosity in 162, but the short answer is when you heat it up, the molecules move faster and become less tangled, so they become more fluid. Whereas if they're colder, they get tangled on each other and become less fluid. In this case, remember, we need to have something to crystallize on. But nothing was present. We dissolved it all. There is no solid sitting at the bottom. And so what ends up happening is we end up in a state called super saturated. So this is what we actually get. We get a super saturated solution. This that we would expect would be a saturated solution. Saturated. So a supersaturated solution is this sort of meta state that you can get by preparing a solution and then allowing it to cool very, 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 very slowly so that precipitation doesn't have a chance to occur. And you get these really interesting effects with this. Let me clear all this out of the way in case you want to read it. And so what happens when we try and crystallize a supersaturated solution? Well, it needs help. We need to have some sort of location in the solution that will allow crystallization to occur. So that can be dropping a crystal in, or scraping the container enough so that the container is no longer perfectly smooth, or even just like shaking it a little bit. So what I have here is I have a video of the recrystallization of sodium acetate, which is really soluble at high temperature, but it's super insoluble at low temperature. And so we'll get this video on the screen here. Good job, OBS. That's exactly what I wanted, just the bottom half of the video. All right. And so I like this video because you can actually see the instructor in the background right here. Oops, can't see my cursor. There he is, right there. He's going to be adding a small crystal of sodium acetate on the end of his spatula to this solution. And when he does that, this is what happens. Remember, this solution is currently supersaturated. So since we've given the solution a place to crystallize, it now starts to do that. And because it's so insoluble at this low temperature, way more of it crystallizes than dissolves. Now, both processes are happening. It's crystallizing and dissolving, but it's crystallizing significantly faster than it is dissolving. And so as an end result, you get this. And it looks really, really cool. Now, you can play with this. I have another video here that I like to show. And so all of these supersaturated solutions crystallize really, really, really readily. Now, crystallization releases energy, so you'll notice that the thermometer read like it's super hot when it does that. The solution is actually at room temperature, but once it crystallizes, it's releasing energy because all these bonds are forming. Now, it is still an aqueous solution, so if you break it out and you look inside, there is water in there. There's just not that much water because it's been absorbed by the crystal structure. So it's kind of like a hydrate. Now, you get some really weird stuff with this. So, like, if you pour it, it expands so quickly because the density of the solution is way higher than the density of the solid that's crystallizing. And, of course, all you need is a surface that has a little bit of crystal on there, and it will recrystallize on its own. Now, if you're not careful, this will happen, which is kind of cool in and of itself. You can see how it's not crystallizing now, although it did start over there. And that's just because it's so saturated. Most of the time, you do need a surface to start it on. And there you go, the end. That was my crystallization video. Not one that I did, but the one that I use a lot. All right. So those are the different states of our solution. We can have unsaturated, which means that there is not enough solute in there and you could dissolve a little more. You can have saturated, which means that the maximum has dissolved and there is excess precipitate at the bottom of the solution. Or you can have supersaturated, which means will crystallize readily, has too much in the solution dissolved for a given temperature. Is blood supersaturated? No, because your blood would immediately crystallize on weird things like it hitting a surface or you eating something and it getting in your bloodstream. So that would be fatal. Your blood is not supersaturated. Your blood is an unsaturated solution. It can dissolve more stuff in there. Yeah, you do not want to be supersaturated. All right, let's talk a little bit about how we make solutions. So the first type of solution that we're going to deal with is aqueous solutions. An aqueous solution uses water as the solvent. A non-aqueous solution would not have water as the solvent. We're not going to deal with that in this class. We're going to stick with water. I don't care about these questions, so I'm just going to skip over them. But let's actually prepare some solutions, or at least attempt to. Now, in order to prepare a solution, we need to know if it will actually form a solution. And so that's where the solubility rules come into play. Now, the rules for solubility are shown here. These are only a few of the ones that you need. I don't ask you to memorize this chart. If it is used on a quiz or an exam, please refer back to this slide. Just have it handy. But what I want you to do is I want you to be able to read and understand this chart. So let's just pick a random compound. I'm going to pick NaCl. So we know that sodium chloride dissolves in water. And what we're going to do is we're going to use this chart to determine that. So the first thing that we need to do is we need to split this into the ions that make up this ionic compound. And we did this in a previous chapter. So you should know that sodium chloride is the Na plus ion and the Cl minus ion. How do we know that these are the charges? Based on the octet rule, which we talked about when we were drawing those beautiful Lewis structures that everyone is so fond of. Once you know the ions that are in the compound that you're looking for, now you got to find them in the chart. So we need to find either sodium or chlorine. So here's chlorine. And sodium is a group 1A cation, so it's also in here too. Sometimes you won't be able to find one of your ions, but you'll always be able to find the other. You just have to look for it. Your ion will fall into either the soluble table or the insoluble table. So whichever one it falls into, that's what it is. So sodium-containing ionic compounds are soluble, unless they are one of these exceptions. You'll notice that the exceptions are none in this case. So anything containing sodium dissolves. What about chlorine? In this case, it's chloride. Chloride is soluble unless it's one of these exceptions. And none of these exceptions that occurred are sodium. So our sample of sodium chloride is soluble. All right, let's do another one here. So let's do AgCl. We'll do that. So we know what ions that forms. And let's look for it again. You'll notice that silver is not anywhere in the ions chart, but chlorine is, as chloride. Chlorides are soluble unless you're paired with one of these, and you'll notice that this is one of the ones that we have. So AgCl is insoluble. Let's do one more. Let's do chalk, calcium carbonate. Here are the ions that it forms. If you ever dropped chalk in water, I don't know why you would do that, but if you have, you probably noticed, oh, it didn't dissolve. Well, let's find one of these things. So is calcium in here? I don't see it. I did see carbonate, though. Carbonates are insoluble unless they are paired with something from group 1A or ammonium. Well, this is not from group 1A or ammonium, so this is insoluble. All right, I think you get the point. That's how we use the chart. Now, how is this happening? We're going to come back to that chart in just a little bit, but let's talk about the interactions between water and the solute. If something is ionic, water will dissolve it if water can form better attractions to the ions than the ions do to themselves. So, water can disrupt the ionic bond. And the way that it does that is by forming its own interactions to sodium. And the reason that water can do this is because water has a property called polarity. We're going to talk about polarity more in 161. But you can think of a polar compound as something that has a partial charge to it. Water is kind of like halfway between an ionic compound and a covalent compound. It's covalent, but it does have charges, and those charges can interact with other things. You can see those charges written on my water here. So each of the hydrogens has a slightly positive effect. That's what the delta symbol means. The oxygen has a slightly negative effect. Well, if I put a bunch of those negatives at sodium, that interaction is better than the ionic bond that sodium would form. And as a result, the sodium dissolves into the solution. Same thing for chlorine, as chloride there. The chloride will just collect the hydrogen parts of the water and dissolve that way too. Now, there are other reasons why this dissolves, specifically entropy. We're not going to talk about entropy in this class. We'll talk about it in 162. But suffice it to say, for ionic compounds, they will dissolve in water effectively if they are the ones that match on this solubility table here. What if my compound is not ionic? What if it's a molecular compound? What if it's something like ethanol or acetone or something? Then we follow this rule. Like dissolves like. Water is polar and dissolves ionic compounds, but it will also dissolve other things that are polar. Now, obviously, you don't know what's polar and what's nonpolar yet because we haven't talked about polarity, so I have to tell you it. So, for instance, if I tell you that oil is nonpolar and water is polar and you try and mix them together, you should get two layers because one is polar and one is nonpolar. They are not the same. Two polar things will mix, two nonpolar things will mix, but polar and nonpolar do not dissolve each other. And we'll get to that again next quarter in 161. So let's do an example of that. I have acetone, which is polar, and water, which is polar. Will they dissolve in each other? Well, like dissolves like, so yeah, they're both polar. What about cooking oil dissolving into carbon tetrachloride? You've probably never heard of carbon tetrachloride, but it's nonpolar. So is cooking oil. Will they dissolve into each other? Yeah, you'll form one solution. All right. What about these compounds that I give you? So barium chloride, will it be soluble? Let's go back to the chart and look at it. So I have barium chloride here. This splits into barium and chloride. And there are two of these, but we don't really care about that because we're just hunting for the ions that we want. Okay, chlorides are soluble unless one of these, but barium is not one of those. So we conclude, yeah, this should dissolve pretty readily. And that's what our answer is. We already did calcium chloride. Or calcium carbonate, sorry. How about ammonium phosphate? I want you to take a second, so you'll have to pause the video and rewind. Or just write down this formula, NH4,3PO4. And then I'm going to put this back on the screen here. And I want you to tell me in the chat, soluble or insoluble, based on the data in the chart. I'll give you about a minute to do that. All right. Let's go over the answer here. So we're looking at ammonium phosphate. And you'll notice that here's ammonium and here's phosphate. Oh no, they're in different sides. What do? Well, let's follow it to our logical conclusion. So ammonium compounds are soluble with no exceptions. Okay. But phosphates are insoluble unless paired with either group 1A or ammonium. Look at that. So it's still soluble. So even if you find it on both ends, they'll both lead you to the same conclusion. Because all of the exceptions include things that are in the other half, in the soluble half. And that's why I give you that example, because sometimes you do end up with both. All right, so I'm going to give you this list of substances. So the first two are just polar versus nonpolar. Tell me if they are soluble or insoluble, those solutions that we're making. The second one might surprise you a little bit, but we'll talk about it in just a second. And then for the last ones, you're going to have to go refer back to that chart. So you'll have to go back a few seconds in the video once you have written all these down. I'll give you about 4 or 5 minutes to come up with the answers. The last question is not meant to be a trick. Okay? We haven't talked about benzene, but I did say that benzene is nonpolar. What do you think will happen with an ionic compound? Yeah, so ammonium phosphate is soluble because the ammonium part is soluble with no exceptions. The phosphates are insoluble, but if you pair it with ammonium, then they are soluble. All right, I'll be back in 5 minutes. We'll go over the answers then. Sorry, I had to go get another soda from there. I'm going to give you more time, but I did want to address this question. So the previous slide said, even though phosphate compounds are insoluble, ammonium is an exception. So when it's paired with ammonium, the substance is soluble. Because it's both things together, right? There, we'll put that back. Let me know if that didn't answer your question. All right, 2 more minutes, so we'll go over the answers, and then we'll take our break. All right, let's go over the answers. So for this first one, like dissolves like, so these are similar. They're both nonpolar, so this is soluble. Benzene and hexane dissolve very easily into each other. Oxygen is nonpolar, and water is polar. These are insoluble. And you might be thinking to yourself, well, wait a second. If oxygen is insoluble in water, how the heck do fish breathe if there's no oxygen in there? And it's not that there's no oxygen, it's that there's very little. Remember, insoluble just means very little if it dissolves. If oxygen were soluble in water, all of it would have been sucked into the oceans by now, and then we would suffocate and die. Alternatively, we would all have evolved as fish people, which could also have been kind of cool. So, you know, your mileage may vary on that viewpoint. I don't know. I think fish people are cool. But there's not that much oxygen in water, it turns out. And in fact, if you heat the water, which is why global warming is not just a crisis for us overheating out here on the land, but also in the water, oxygen becomes less soluble as temperatures in water go up, and the end result is that fish suffocate and die. And we don't want that, because we want to eat fish, right? All right. Sodium nitrate and water. So I'm going to write all these down real quick. So let me put them on just this sheet here. So we got sodium nitrate, potassium sulfide, lead 2 chloride, barium hydroxide, and NaCl. Oh, NaCl and benzene. Okay. So we'll come back to that one. But let's go back to the chart. There's our chart here. So the first one that we have is sodium nitrate, so NaNO3. And so you could find nitrate right here, or you could find sodium in this right here. They're both soluble with no exceptions. So NaNO3 is soluble. All right, let's do the next one. The next one was K2S. So potassium's up here, but sulfide is down here. Sulfide is insoluble unless paired with a group 1A, which is what potassium is. So this is soluble. Sulfides are normally insoluble, but when you pair them with things like potassium or any other group 1A cation, they are soluble. All right, let's clear that out and do the next one, which was PbCl2. So lead is not in the left column, but chloride is. Chloride is soluble unless paired with So it changes to insoluble. And then the last one we have in this chart is barium hydroxide. So no barium on the chart, but hydroxide is here. Hydroxides are insoluble unless paired with one of these, and here's barium. So it changes too. So instead of insoluble, it is now soluble. There you go. So that's all of those. So let's go back to this slide and we'll write all the answers in real quick. So this was soluble, soluble, insoluble, soluble. All right, NaCl and benzene. Sodium chloride is an ionic compound, and benzene, like we said above, is nonpolar. If something is nonpolar, will it dissolve something ionic? Well, what dissolves ionic compounds? Water does, and water is polar, right? So if water and NaCl will dissolve, but water and benzene would not dissolve, would sodium chloride and benzene dissolve? And the answer is no. So if this works, and this doesn't work, then by extension, these two cannot dissolve in each other either. Because like dissolves like, right? All right. That is the solubility section. So when we come back from the break, what we're going to do is we're going to talk about prepping solutions and using numbers and assigning stuff to it like that. So we'll do that in 10 minutes. But for now, go grab some more water or a snack, or go outside and pet the cat. I don't know, whatever it is that you want to do on your break. And I'll see you in 10 minutes. Alright, we are back. Let my creepy music fade out here. That's one of my favorite soundtracks, is this game. I would strongly recommend anybody who has an interest in any RPG to play Nocturne. It just got re-released on Steam. And I can't play it because I don't have Windows 10! Ugh. I could go play it on my PS2, I guess. But it's so good. Okay, but enough about that. Because I could talk about that for hours and hours. Instead, we're going to talk about concentration and molarity. Boo. But we're going to introduce the concept of molarity. Molarity is that weird M unit that was on the bottles of the salt solutions in the conductivity lab. So you probably noticed that, like, oh, I gave you 0.1 M and 1.0 M and 4.0 M. What does the M mean? That's what we're going to talk about today. So, first let's define concentrated versus dilute. If I have lots of solute in a solution relative to another solution that has less solute, the one with more is concentrated and the one with less is dilute. So in these pictures here, and this is not exactly clear, so let me indicate this. So these blobs, these are my solute, and then the space is the water. So the water is everywhere, and we've sort of ignored it in the picture. On the left solution, I have a darker solution because there is more solute. It's more concentrated. The one on the right has less solute in it, so it's less intensely colored. And so we call it dilute, because there's less solute in there. The amount of water in both of these is roughly the same. Alright, how do we calculate the concentration of the solution? That's where this M thing comes in. This is called molarity. Molarity is a very specifically defined unit. And you'll notice that I've color-coded these so that you notice them and are careful with them, because notice what's on the top. We have solute on the top and solution on the bottom. Solvent does not appear in this expression. Don't use it, okay? So if I tell you, oh, I mixed this much and this much together, double check that you are picking the correct one for the solute and the correct one for the solution. Okay? That's a real common mistake, because people might think, oh, I'm going to add 100 milliliters of water to this, and then my volume is 100 milliliters, neglecting the fact that the solute that you've added also has a volume too, right? So if you add 100 milliliters to a little pile of salt, you end up with more than 100 milliliters, because the salt takes up some space too. Not very much, because it dissolves, but it does take up space. So we care about the end result. That's the solution. Okay? So don't measure out your water beforehand. Measure it out in the process of making the solution. And that's part of what this section is going to teach us, is how to make a solution, what the proper steps are. Now, we've seen these units before. We've dealt with moles a lot, and we've dealt with liters a lot. So this should be pretty trivial to figure out molarity, especially when I give you an amount just in moles right there. So if I have a solution with 2 moles calcium chloride, and its total volume is 1.75 liters. Notice how I didn't say it was mixed with 1.75 liters of water. I said mixed with water to form this much solution. The language is specific here, and it's going to be important. When I throw that in the calculator, I have to actually get my calculator because I didn't need it for my other classes. I get 1.1428. So 3 sig figs, that's 1.14 moles of calcium chloride per liter. Which I could also write like this, 1.14 capital M calcium chloride. The capital M means molar. So I have a 1.14 molar solution of calcium chloride. Or, in other words, there is 1.14 moles of calcium chloride per liter of solution. And so that's where the capital M comes in. So now if we go back to those solutions from the the conductivity lab, and you look at the bottles and you see 0.1 capital M NaCl, that means there was 0.1 moles of sodium chloride per 1 liter of that solution. A 1 molar solution would be 1 mole of calcium or sodium chloride per liter of solution, and 4 molar would be 4 times that. So that's how we calculate molarity. We're going to be using grams, obviously, instead of moles, but converting from grams to moles is something we did in like units 12 and 13 and 14 and 15, so we're not going to deal with that right now. I'm going to assume that by now you know how to convert moles to grams, because we're going to do it again in a second. We'll do the calculation. So let's suppose I wanted to make that 1 molar solution. I want to make the solution for the video. And so I'm going to give you the following things. I'm going to give you infinite water. All the water you want. Just turn the faucet on, right? I'm going to give you infinite sodium chloride because Everett Community College can go to the Costco and buy a big bag of sodium chloride and provide you with all you need. And we're going to give you a 1.0 liter volumetric flask. What is a volumetric flask? A volumetric flask is one of these flasks that looks like a potion bottle that you'd see in like a fantasy game, or kind of like a bong, I suppose, if that's your thing. But on the lip of it is a specifically written mark that indicates the volume when you land on that line. And it's very specific about this. So this is this part zoomed in. Here's my mark. And so what I want this to do is when I fill this with water, my water is going to land on the mark. And I've sort of exaggerated in that drawing, but what you'll end up with is you'll have something that looks kind of like that. Now, water curves in a glass container because water is polar and the glass that is made is actually also polar. So they're attracted to each other. The water climbs up the side of the glass. This is called a meniscus. When you prepare a solution, the correct technique is to have the bottom of the meniscus touch the top of the line. If you've done that, you have prepared a solution with volume 1 liter in this case. Now, if you're down here, you have less than 1 liter. And that's an easy fix. You just add enough water until you do that. But what if you add too much? If you add too much, now you have more than 1 liter, and you can't pipette it out because any solute that's in there would get pipetted out with it, and you would have a lower molarity than you intended because you've removed some of the salt that you added. So if you add too much, you have to dump everything out and start over. It's game over, return of Ganon. So don't do that. Add your solution carefully so that it lands on the meniscus and you don't overshoot it, because if you go over, your solution is ruined. Yes, it's ruined. Alternatively, you could recover the solution by boiling away the water or letting it evaporate. That's extremely tedious, so it's faster to just dump it out. All right, that's the premise behind what we're going to do. We're going to put salt in, however much salt we need. So there's my NaCl. Then we're going to fill it to the line with water, and then we're going to mix it really well. Okay, let's do a calculation to show how much we need. Oops, so you get to see my notes here when I was writing down all of those for the solubility. So I want a 1 molar NaCl solution in 1 liter. So let's write down the equation for molarity. Molarity is equal to moles of solute over liters of solution. And I know that I want 1 molar sodium chloride and I want 1 liter of it. So I can solve for moles of solute. So the number of moles of solute will be equal to the molarity times the volume of the solution. We're going to change this equation a little bit later to be this. So I'll just introduce that to you now. So I would get 1 mole per liter NaCl. That's the molarity times the volume, 1 liter. And you're probably thinking, well, that's the easiest calculation ever. So I need to put 1 mole of sodium chloride in there. But I don't have a balance that weighs out moles. So what I need to then do is do the conversion from moles to grams. And we can look up how many grams there are per mole on Lentech, right? So that's 58.44. So in order to do this, I would need 58 grams of sodium chloride to get a 1.0 molar solution. So there's my calculation. I have figured out the mass that I need, so now I need to prepare the solution. So let's do that. So step 1, add 58 grams sodium chloride to a 1.0 liter volumetric flask. So we'll draw my flask here. Here it is. Well, it got a little wide there. I guess it's been drinking too much beer during the pandemic. Asking for a friend or something like that, right? Okay, so we're going to weigh that out. There's my sodium chloride. It sits in the bottom. That was step 1. So we got it in there. There's my mark there. Step 2, add water to the mark. And we're going to get rid of my pink that I've been using for the last few days. We're going to replace it with a color more appropriate for water. So I'm going to add water. Whoop. There we go. We've added water. And then the last step, this is very important. Mix it really well. I've put 50 times in there because what you would do is you'd put a lid on this. You'd put the stopper in here. And then you would invert this 50 times. And what would end up happening is that all this salt that was at the bottom would then distribute out evenly through the mixture. And once you've done that, you have made the solution. Now there is a secret 4th step. Enjoy. You're not required to enjoy, but students like that because it helps them remember, I guess. I don't know. So that's how we prepare our solution. And so when I go back here, you'll see that I've got a little picture that does that for you. Now, there is a little bit of nuance to how to do this, and I wish that we'd get to practice it in the actual lab. But when you're adding a solid, so here's my solid, I poured it into a graduated cylinder of all things. But when I pour this in here, not all of it's going to come out. So this water actually needs to rinse all of the sides of the container that was used to dispense it, as well as the funnel. So rinse that all with lots of water, making sure that all the rinsings go into the flask, because the rinsings will have the trace amounts of sodium chloride that are stuck to the container sides that didn't quite make it. Once you've rinsed all that in there, you're going to fill the remainder to the mark right here with water. So we'll just keep going. And then once it's there, you're going to cap the solution and you're going to mix the hell out of it. And this is actually the most crucial part. Believe it or not, if you forget to mix, it's like you didn't make a solution of 1 molar at all. You're going to get something that's super dilute at the top and then very concentrated at the bottom. Now, people have actually done studies of how many times you need to invert your solution in order to make it homogeneous. And the magic number is 50. So what that means is that you just have to sit there and stir your solution by inverting it up and down for about a minute. And I have students that do that in the lab and they're like, "Oh my god, this is so tedious." And I'm like, "It's 60 seconds. Just fucking do it, right? Just stir the solution. It's not torture." Torture is the rest of this class. That's what we're doing to you. Sitting and inverting a solution is not that bad. But you do have to do it, because otherwise you don't get a homogeneous mixture. And we want a homogeneous mixture. Otherwise our experiments will not be reproducible. Alright, so that's how we make a solution if the solute is a solid. So what I want you to do is prepare this solution. Oops. I want you to make a 3.5 molar solution of KBr in water. You're going to need to go to Lentech to figure out the molar mass of KBr, or consult a periodic table if you have one handy. I still want 1 liter of solution, so first tell me the mass of KBr that you need using the molarity equation and converting it from moles to grams. Then describe, using the 3 or 4 steps that we just talked about, how you do that. So write it out. Step 1, I would do this. Step 2, I would do this. Step 3, I would do this. Step 4, enjoy. Just like that. I'm going to give you 5 minutes to do that, then we'll go over the answer, and we'll see where we're at after that. Back in a bit. All right, one more minute, we'll go over the answer. All right, let's go over the answer here. So let me clear this out real quick. All right, let's make this solution. So I need this concentration of my solution, and I want 1 liter of it. And we know that molarity equals moles of solute over liters of solution. And I know that this is the concentration and this is the volume. So I'm going to rearrange my equation. So this is the molarity. So molarity times the volume equals the moles of solute, which is 3.50 moles of KBr per liter times 1 liter equals 3.50 moles KBr. But of course, I don't want moles of KBr. I want grams of KBr, right? And in a mole of KBr, there are, I don't know, I have to look that up. (119 grams per liter). And for some reason, I have this number memorized. Although it was just posted in the chat. I know that that's the answer. 417 grams of KBr. Okay, so now we know how much we need to weigh out, so let's get our flask out. So here's the flask. It's a little dented, but that's okay. There we go. And we're going to step 1. We're going to add 417 grams of KBr to the 1 liter volumetric flask. All right, there it goes. Bloop, there. And then step 2, we're going to add H2O. I didn't put the fill line on it. There it is. To the fill mark. So I'm going to add my water. Bloop, there we go. And then step 3, mix really well, 50 times. And then, of course, enjoy. And once that's done, your solution will be homogeneous. All right, that's how you do it. Any questions, let me know. So now you've probably noticed that this formula up here, MV equals moles. Oops, I changed away. This formula up here, MV equals moles, can be used to figure out the amount of moles in any amount. So like if I didn't want to do 1 liter, I could do 0.5 liters or whatever. So we're going to do that on the next slide here. So if you know the volume of the solution and you know its molarity, you can figure out how many moles are in that sample, whether that sample exists or you're calculating it to figure out some future solution that you're going to make. So for instance, let's suppose that you had 0.350 molar magnesium hydroxide, and you have 500 milliliters of it. How many moles are in there? Well, if we know that MV equals moles of solute, then I could say 0.350 moles magnesium hydroxide. Let me get rid of that because that's a misstroke there. Divided per liter. There we go. Times the volume that we're looking at. Wait a second, these don't cancel, right? So milliliters is a really common unit to be working with. Make sure that you aren't just blindly entering numbers in your calculator. The units have to match because these don't cancel. So I can't use 500 milliliters. I have to turn this instead into liters. And now they do cancel. And so now I will get the correct number of moles, which looks like 0.175 moles magnesium hydroxide. All right, so that's where we're going with this. We're going to be using this basic definition of molarity to start solving for quantities in solutions. That's going to become important in tomorrow's lecture when we do dilutions and then finally do some stoichiometry with them, okay? Let me clear that so you can see it. There's the answer. So I'm going to leave these problems for you to try for practice because we don't have enough time to start them and then finish them. But we can begin here tomorrow, and then we'll do dilutions real quick, talk about the lab, and then we'll do the stoichiometry, which is the last part of the lab. And then we're done. That's it. So there's one more day of content left. Probably won't need to use any of the review period for lecture. I'm expecting that we'll get everything done tomorrow. So I'm going to leave these problems for you to practice. We'll start tomorrow right here by beginning with these problems. My cat is upset with me. I haven't been paying attention to him today because I've been spending all day teaching. But I will go and pay attention to him now, and I would encourage you to do the same. Yes, please pay attention to my cat, or your cat, or any cat. Just cats in general, right? All right, I do want to thank everyone for coming out to the lecture. There were actually people tonight. It was nice, as opposed to last week when it was lonely and sad. Make sure that you do the course evaluations. Make sure you get quiz number 8 up and finished. It's due tomorrow. We'll see you again tomorrow for the final lecture. Take care.